So I'm Jared Chandler. I'm a PhD candidate at Tufts. I'm really excited to present this work. Our tool is called BinaryInferno. This is joint work with my colleague Adam Wick and my advisor Kathleen Fisher. In terms of what I'm going to cover today, I'm going to start off with just a brief introduction into why people reverse engineer protocols. I'm going to introduce our approach to perform this, and then I'm going to talk briefly about our evaluation, which showed a significant improvement over existing methods. And then finally, I'm going to conclude just by talking about some of the limitations of our approach and where we look to go with future work. So why do people reverse engineer protocols? Probably for the same reason that they reverse engineer programs. You want to understand, is this thing malicious? Is there a security vulnerability in it? Maybe you have a specification and you're not sure it actually adheres to the specification. Maybe it's something old that you thought nobody's going to be using this in 30 years, and it turns out like it's a critical piece of infrastructure. Maybe you just want to see what's on the wire to make sure something bad isn't being exfiltrated or brought in. So our work focuses on what we think of as pure binary protocols. Those are just protocols unlike HTTP, Telnet, or XML-RPC, where you can't just look at it as a string and figure out what's going on. It's ambiguous binary data. The same bytes could be an integer, they could be a float, they could be something else. And that's what makes it difficult to actually reverse engineer them. So there's a number of approaches that currently exist to perform this reverse engineering, but generally they rely on different artifacts. You got to have a copy of the source code to look at to do an analysis. Maybe you need a running binary that you can actually like instrument and see like how does it like manipulate the data. Or maybe it's a hardware device you need to actually put on the network and fuzz to find out like what is it doing. And in the worst case, you just have a human who's going to like look at the that should be a little pic. Oh, supposed to be a human there. You have a human who's supposed to look at the data and figure out, hey, what's going on? Like what is it? And that's a process that could take days, weeks, sometimes months. One solution to that is to try and develop automated systems that can sit somewhere in between, that they can look at the data going across the network and have a hypothesis as to what it describes and pass that on to a human. So what's new about our approach? We had this insight that even though like you can create like, any binary protocol you want, but because these protocols need to be deserialized unambiguously, quickly, and usually in a single pass, they're actually quite constrained. That binary protocols tend to reuse the same atomic data types. They tend to reuse the same common serialization conventions. They tend to use like unions and loops. And by looking for these things, we can uncover traces in the protocol, little clues in the actual values that are transmitted across the wire. And if we pick up enough of these clues, we can have a pretty good idea of the format of the data like actually being transmitted. And that's the intuition behind BinaryInferno. BinaryInferno takes a set of binary messages like this, and it automatically infers a format that can then be used to divide the messages into fields, and where possible, if we've recovered some sort of semantic information, display that to the analyst to give them context into what's actually going on. Then the only thing they have to do is concentrate on the unknown parts. We've already done a lot of the heavy lifting. So I'm going to talk about our approach in two phases. In the first phase, we use an ensemble of simple detectors to look over these messages and look for clues. We're out there searching. In the second phase, we take all these clues and effectively we put them on the bulletin board, and then we use the red string to try and put it together and figure out, hey, like what actually happened here? What's the mysterious format that we're looking for? The model of our detectors is simply they're simple programs that look over a vertical slice across the messages and try and make a decision as to whether or not this slice corresponds to a particular type. And as they move across, eventually they find, hey, like I think this region right here, I think this is a field of some type, maybe a float. We move them across the entire range of messages, and they find all the clues. So what are some of these detectors we've got here? We've developed detectors for some common atomic data types, things like floats, length fields, timestamps. We've developed a specialized serialization pattern detector that searches for common serialization patterns over regions of binary data. And in both cases, we know something, we know like what is an atomic data type, and we know what is a common serialization format. But what if we don't know that? What if it's data we've never seen before? Well, we can't just give up. We still got to make progress. We got to do something useful for the analyst. We use a Shannon entropy approach to identify field boundaries for data we haven't previously seen. So I'm going to talk just about 3 of these here, the ones that I think are most interesting, and maybe to give you a sense of these detectors. They can be written independently. You don't have to use the same method for every one. They can use whatever method is best specialized to like the particular type of data you're using. So for our float detector, we analyzed distributions of IEEE 754 floats, and we found something interesting. Like you think like a float, it could be like something like on the, astronomical scale, or it could be like, subatomic. Well, float values that are relatively close together tend to reuse the same exponent. And if you look over the distribution bits in a collection of floats, you're going to see this really interesting pattern where the frequency of the most common bit in the exponent is just about double the average bit frequency of the bits used in the significand or mantissa. And that characteristic profile is something we can go and search over slices in a message to identify where we think possible floats are. For serialization patterns, we took common serialization patterns that we observed in data. Like the most common one is probably length value encoding, where you first distribute you send the length of the value, and then you send the bytes that make it up. In this case, you send 5, and then you send the characters for zebra. We created a serialization grammar that covers a whole slew of these patterns. Then when we have a set of unknown binary data, we can perform a search over it. Our search is pretty simple. We start off by saying, let's get a pattern from our grammar. Let's try applying it. Let's interpret the data according to that pattern and see what happens. If we have bytes left over that the pattern doesn't basically consume, we recurse. We try and fit another pattern onto those remainders. And if any of the patterns we apply try to read too much data, if they basically index into unallocated memory, we're like, nah, that's not good. Can't use that one. Pull it off and try something else. So when we have a pattern or a sequence of patterns that exactly describe all the bytes in a message, we return that as a possible solution. Okay, so what happens when we don't know anything about the data? Well, we observed that you can still make progress. You can still find signal deep down there and collect a clue that will be helpful to an analyst. We use something called Shannon entropy. Shannon entropy is a way of measuring the amount of information in a set of observations. So by looking for pairs of adjacent bytes where there's a sudden shift in the amount of Shannon entropy, we can infer where a field boundary possibly exists, even if we haven't necessarily seen the underlying data type. The intuition here is when you think of the 4-byte representation of an integer, the most significant byte is used the least frequently and therefore has much less information than the least significant byte. Okay, so we've talked a little bit about how we go through and collect the clues. How do we put them together? We start off by taking all the clues we found and we create a graph. We introduce each of the fields we found from our ensemble as a node in our graph. We then create edges in our graph between any pair of fields that could be read sequentially. Basically, as long as they're not overlapping in any way, because that's a sequential read. And we weight these edges by the amount of data each field describes. So in this case, this length field of 2 bytes has a weight of 6 because there are 3 messages. So that means if we read this field, this length field, we're going to read 6 bytes of the description. The intuition here is we want to search through this graph. We want to find all the clues that describe as much of the data as possible. We want to find a way to maximize the description we return to the analyst. So after we've created this graph and we've weighted all of our edges, we just need to find a max path across the graph from the source to the sink. And we can do that quite quickly. Once we found that, we extract the edges and we return those to the analyst as the final inferred description. Okay, so I've told you a little bit about how this thing works. Let's talk about how it performs in the real world. When we chose to evaluate our tool, we had to decide what are we going to evaluate it on. We chose identifying field boundaries. So protocol reverse engineering is a pipeline. There's a bunch of different tasks. You have to cluster the messages. You have to identify field boundaries. You have to identify field semantics. Once you've identified the field semantics, then you can start looking at, can I infer a state machine that describes the protocol? But we focused on identifying the field boundaries. This means we want to have a crisp understanding of where each byte in every message belongs in terms of fields. We chose to evaluate our tool and some other tools on 10 samples from 10 different real-world protocols, a bunch of network protocols, a couple of industrial control protocols, a drone protocol, Mavlink, some samples of malware command and control traffic, and most notably, one protocol we found that was a tutorial protocol used to teach humans how to reverse engineer protocols. We thought that was interesting because that's kind of like the hello world of like protocol reverse engineering. Like, if you can't reverse engineer that protocol, like how good are you? And that's a really interesting idea of like, is that a good metric for all these different approaches? We selected all the tools we could find out there that did that were able to do field segmentation or field inference. Some of these tools do more than that. They have other capabilities, but we decided just to compare on this one task to start out with. So how did it do? Here we present our results for our evaluation on top level protocol samples. We decided when we were going to run our tool, BinaryInferno, we were going to run it in 2 modes. In the first mode, we wanted to run it and check, like, we're not going to tell it anything. How does it perform, like, knowing nothing about the world? And then we were curious, well, what if we give it 1 or 2 facts that might help it? And the 2 facts we chose were, let's tell it the underlying endianness of the data. Is it big endian or little endian? You know, network byte or not? Thank goodness there's only like 2, right? You know, rather than like 8 endians. And then we also told it the approximate time span when like packets were captured. So like a window, a range. And we found that actually like a range as wide as 2 years is sometimes sufficient to identify timestamps. In terms of the chart I have up here, we plotted the average performance of all these different tools. The y-axis is precision, the average precision of a tool. The x-axis is the average recall. And I'm going to point out that goal square up there, like top right. That is perfect precision and perfect recall. That is what you want. You want to hit that box. That means you got every single field you found, you got it right, and you found every single field. And as you can see, BinaryInferno and BinaryInferno with priors indicated as BI plus were significantly closer to that than any other tool. They did much better in this task than like any of the other tools we evaluated. We found also that like as we added more messages, as you went from a message sample size of 100 messages to 500 messages to 1,000 messages, our performance improved. So that's great. I've shown you a chart and I've shown you a table, but like, what does that mean to like an actual analyst? So let's look at it from an analyst's perspective. Remember that tutorial example I talked about? Here we have the ground truth for that tutorial example. We've color-coded the fields, and the true field boundaries are indicated by the thick black lines. Here's the descriptions produced by some of the other tools we evaluated. The thick red lines indicate a false positive, where the tool thought there was some boundary when in fact none was there. And if you see 2 adjacent colors that are touching and there's no thick black line, that means the tool didn't infer a field boundary. Some of those are pretty good, some of those not so good. They're kind of all over the place. By comparison, BinaryInferno and BinaryInferno with priors did much, much better. And in the case of BinaryInferno with priors, it exactly matched the underlying specification. How long do these things take? It's an automated process. It's no good if it takes years. Thankfully, everything in our evaluation finishes in the time scale of like seconds to minutes. So these are all things that are like certainly within reason for an analyst. They could go get a cup of coffee and like come back and see what the tool has produced. I will note that like we analyzed what caused the time performance of BinaryInferno, and the greatest contributing factor, the thing that really pushes our time up, is our serialization pattern search. That's the search exhaustively over all the different combinations in that grammar. All right. It's not without limitations. Right now, the biggest limitation is BinaryInferno only infers fields or serialization patterns that are common to every message. Many protocols use unions over payload types, and that's something we're currently working on, and we think we have a solution for some upcoming work. As I said early on, we use an ensemble of detectors. We don't claim that our ensemble is by any means complete, and it's wonderfully extensible, and it's very easy to write a new detector, throw it into the ensemble, and have all the recognition capability that it brings. And similarly, it's easy to add new serialization patterns to our pattern search grammar. So in conclusion, I've introduced our approach to automatically reverse engineer binary message formats, which we call BinaryInferno. I've talked about how it's implemented, and I've given you a taste of like our evaluation. There's much more detail in the paper, and I'm also happy to talk to anyone who's interested in this after the talk. We are going to release this as open source in April. And if you're interested and you really want to get your hands on it, if you visit binaryinferno.net, there's a little form. You can give us your email address and we'll let you know when we put it up on GitHub.
I wondered if you considered patterns where you have the value and then you have a checksum over the value.
The question was, have we considered patterns where we have a checksum?
In particular, reversible checksums, where by inverting the checksum, you could actually check if the value is there.
In fact, yes. Actually, an undergrad that I supervised worked on exactly this problem, and we made some progress on it. We chose not to include it in BinaryInferno as a detector right now, simply because that particular process is incredibly time-consuming. And our thought was, first, you should knock out all the low-hanging fruit, and then when you have an unknown region that you don't have an explanation for, then you should move on and pass that off to something that's more time intensive to try and resolve that. But thank you for the question. That's a good question.
Wes Verdiger, ISI. I have many questions, but I'll find you later, trust me. I run a large operational DNS root server. It's one of my job responsibilities. And one of the things we see all the time are sudden shifts in the way, protocols are actually used. Have you used this, or have you looked into, comparing and contrasting? We're suddenly seeing new data in a protocol or maybe hidden messages or, things like that, or data exfiltration to see if you can, suddenly find shifts that didn't used to be there.
Thank you for that question. We haven't done that evaluation yet, but that is certainly a use case, and that is certainly something we're very interested in. I'm also giving a laser talk tomorrow, where I'll talk about a lot of the experimental aspects of this. One of the problems with some of this research is just data like that is sometimes sensitive, and it's hard for us to get it to actually evaluate on. But that is certainly a use case we're interested in.
Jeremy Epstein, National Science Foundation. Really interesting talk. The protocols you looked at are mostly either relatively new protocols or old protocols that are still being maintained and evolving and things like that. I was wondering if you tried some really old protocols, how it would behave, and whether that might be useful for an adversary who is trying to develop protocols that would be harder for you to figure out. And I was thinking, because of stuff I've worked on when I was young, Novell NetWare, which had bizarre protocols underneath the hood.
Thank you for that question. I will tell you, anything we encounter that is hard is usually kind of interesting. Like DNP3, for example, does some interesting things where it sticks checksums. We haven't done too many old protocols, and again, this is just a question of where can we get the data and what is really representative of maybe the use cases we think are it would most commonly be applied. But it's certainly something we're interested in. And specifically, this approach generally is focused on things at the byte level. We're also interested in taking it down maybe to the bit level. That would of course cost more time, but we think that might let us make progress on some of those older protocols you're talking about.